So in the previous videos, we saw how sort of addition of a complex variable with a complex constant can be thought of as translations, and multiplication of a complex variable with a complex constant can be thought of as rotation and scaling of the complex plane. And we saw that with the example of a unit square, but the effect is sort of global. Like when we are adding a complex constant to a complex variable, the effect is translations of the whole complex plane. In the sense, we can think of just shifting or pulling the complex plane by the amount by which we are translating, or rotating the axis itself. And from that perspective, the figure that we are looking at sort of looks either translated or rotated and scaled depending upon the particular operation we are performing. So these are very interesting ideas that come up quite often. Sort of another equation that arises quite often in the study of complex functions is the equation for a circle. So in this video, let's sort of see what the equation for a circle in terms of complex variable looks like. Let's just recall a couple of ideas we've already talked about, which is given a complex variable z of the form x plus iy, its conjugate we defined as z bar is x minus iy, and we also define the modulus of z as square root of x square plus y square. We can also write this as modulus of z square is x square plus y square. Now there's, in fact, if we check the product of z and z bar, it turns out that the product of z and z bar is actually equal to modulus of z square. So let's just check that quickly. So let's check z times z bar, that is x plus iy times x minus iy, and this is x square minus I times xy plus I times yx minus I square times y square. This cancels out. I square is minus 1, and so this gives us x square plus y square. And from here we know that modulus of z square is actually x square plus y square, so this is modulus of z square. So this is a very useful relation to remember, that modulus of z square is actually z times z conjugate. Okay, so now let's see what is the equation for a circle in the complex plane, or in terms of complex variables. So given this two-dimensional plane, we know that, let's say we have a circle centered at the origin of radius r. And let's label the real axis as x and the imaginary axis y, or rather the real variable along the imaginary axis as y. Then the equation for a circle, if you recall, is actually x square plus y square is equal to r square, right? So in this case, we know that modulus of z square is actually x square plus y square. And therefore, the equation for a circle can be written as modulus of z square. Equation for a circle centered at the origin can be written as modulus of z square is r square. Or in other words, since modulus of z is always positive, we can write modulus of z is r. So this is the equation for a circle centered at the origin of radius r in terms of the complex variable z. In the same way, we can think about writing what is the equation for a circle, let's say, which is not centered at the origin, but whose centers is maybe x naught comma y naught and radius r. So how do we write the equation for this circle? And again, the idea is that the equation, a circle is essentially the locus of a point which is at a fixed distance from the center, and the fixed distance is r. Now we know that mod of z for a vector, so in the complex plane, mod of z is actually the length of the vector from the origin to the point z. So if we are to derive the equation for a circle, let's say centered at x naught y naught, what we want is, and let's say the variable along the circle is z, and let's call the center z naught, which is on the point x naught plus I y naught. So the equation for a circle can be simply written as the locus of a point, z is the point that we'll move along the circle. So the locus of a point which is at a fixed distance from the center. Or in other words, we can say that the equation for a circle is that mod of z minus z naught is r, right? Because z minus z naught represents the vector going from z0 to z. That's the vector z minus z0, and we are saying that the modulus of this vector is a fixed number r, which is the radius of the circle. So let's see whether this matches our the equation of a circle that we're more familiar with in terms of Cartesian coordinates. So mod of z minus, if mod of z minus z0 is r, then mod of z minus z0 square is r square, right? Now what is modulus of z minus z0 square? So if we know z is x plus iy and z0 is x0 plus iy0, then z minus z0 is the vector or the complex number x minus x0 plus I times y minus y0, right? And now we want to calculate modulus of this this vector squared. So one of the ways for calculating modulus is to multiply this with its complex conjugate. So let's do that now. So this is mod of z minus z0. So what is the conjugate of z minus z0? Is the conjugate of z minus z0 whole expression, right? And if you recall the definition of the conjugate, essentially what we'll do, we'll take the imaginary part and flip the sign of the imaginary part. So conjugate of z minus z0 is x minus x0 minus of I times y minus y0. And the reason sort of I'm trying to do it this way is also to just to give to sort of get more used to using different kind of manipulations to arrive at the same result. We could simply have taken the modulus of this and without going through the conjugate, but I think it's just a useful exercise to also check how the conjugate works. So the conjugate of z minus z0 is actually x minus x0 minus y minus y0, and you can actually check that this is in fact equal to the conjugate of z minus conjugate of z0. So if you have a sum of variables and you conjugate them, then you have the sum of the conjugates. Okay, so we have this as conjugate of z minus z0, and now in order to calculate the modulus of z minus z0 square, we can use the expression z minus z0 times z minus z0. So z minus z0 is this. So let's work this out. This is x minus x0 plus I times y minus y0, and then we multiply this with its conjugate, which is x minus x0 minus I times y minus y0. And then if we simplify the algebra, again we have x minus x0 square multiplying these two terms, then minus of I times y minus y0 times x minus x0, then we have plus coming from this I times x minus x0 times y minus y0, and then we have minus I square, which is plus 1 y minus y0 square. So these two cancel out, and then we are left with the expression x minus x0 square plus y minus y0 square. And our claim was that the equation for a circle centered at z0 with radius r is mod of z minus z0 square is equal to the radius square. So this is equal to r square. Now if you remember this expression from basic geometry, then x minus x0 square plus y minus y0 square equals r square is actually the equation for a circle centered at the point x dot y0 and with radius r. And so essentially the expression mod of z minus z0 square equals r square is consistent with this particular equation for a circle, in this case in terms of complex variables. So these are very useful expressions to and equations to remember because they arise quite often in the study of complex variables. So yeah, let's sort of talk more about these ideas in future videos, and see you soon. Thanks.